We analyze the pipe flow using energy equation from our previous lectures. However, we haven't looked at the forces generated in fluid flows. These forces are generated due to the sudden change of pipe sections, like diameter change, junctions, bends, and so on. In addition, we can relate the impact of jets on surfaces. In solid mechanics, we use famous F equals ma to find the externally applied forces. However, this is just a simplification. But we know we derived this F equals ma famous formula using the momentum principle. Can we use the same momentum principle to fluid mechanics? Well, no matter whatever the phase of the matter, whether it is solids, liquids, or air, the momentum principle is generic. Therefore, we can apply the momentum or the conservation of momentum to fluid mechanics. Let us state the conservation of momentum for fluid mechanics. The rate of change of momentum of fluid flow in a given direction is equal to the sum of the external forces acting on the body of fluid resolved in the same direction. Now, the fluid flow in a given direction is very important, as well as the forces resolved in the same direction. They are two most important factors here, because we all know that momentum is a vector. Therefore, the direction is highly important in the momentum principle. Thus, in fluids in motion in three-dimensional frame, we can define three types of momentums: mx, my, and mz. Now we know in solid mechanics, momentum is mass into velocity. So mx goes to mass into velocity in x, whereas my goes to mass into velocity in y direction. Similarly in the z direction as well. Now let us see how we can mathematically express the momentum for flowing fluids. Now let us consider the same stream tube as the control volume. Now we know, consider the surface 1 and surface 2, where we have the flow through these two surfaces. We can do a bit of mathematics as shown here using the vectors, and can obtain the momentum flux or rate of momentum as m dot is integration over the area v rho v dA. Therefore, we can find the external force, see the rate of change of momentum. So we need not only the momentum flux, we need the change of momentum flux. Let us write this change of momentum flux from the surface 1 to surface 2. So we'll get the momentum flux of surface 2 and subtract it from the momentum flux for the surface 1. So F is therefore integration over the area 2 v rho v dA minus integration of area 1 v rho v dA, considering the directions. Therefore, we need to include the direction to the equations. Now, with a bit of mathematics, we can obtain a simple equation. We know the continuity equation. So, let us use the continuity equation and derive the momentum principle for the non-branching networks. That is, F is equal to rho Q V2 minus Vx. You can see the x directional component here. Now, please go through these simple calculations, simple mathematical calculations, and obtain the expression. Now, if we have a branching network, the equation is slightly complex. It is the external force F is equal to sigma rho Q I V I goes from 2 to n minus rho Q1 V1. And also we know that sigma I goes from 2 to n is equal to Q1 from the continuity equation. We can apply this simple equation to find the real world systems, the forces acting on the real world systems. Please remember, we might have to incorporate the outcomes from the energy equation. And now we can find the forces in the nozzles like this, where we have the sudden contraction. Then we can find the forces, the external forces due to the impact of these jets in different directions using the momentum conservation. That's it.